Today's lesson is on a special situation with probability. As you can see at the top, it says the probability with two outcomes, binomial probability, and it's named after a mathematician, Jacob Bernoulli. So these are typically called Bernoulli trials. And what happens in Bernoulli trials, or in a binomial experiment, is we have two mutually exclusive outcomes. Those outcomes are what you're looking at either happens or it does not happen. But additionally, in a Bernoulli trial, you're going to look for multiple trials of the event. We call them trials. So multiple runs of the event, or you just keep doing whatever it is over and over. So if you're shooting 3 free throws, it might be 10 free throws, and I'm going to look for a certain probability. Or if I'm looking at the probability it will rain, I just don't want one day, but I want to know out of 20 days, what's the probability it will rain half of them. So there's multiple trials of the same event. And that's what differentiates Bernoulli from doing just simple probability. So we're going to call the probability of success P, and we're going to call the probability of failure Q. Let's look at a situation of those. If we flip a coin and heads is success, then the probability of heads is 1/2, and tails would be considered a failure, but its probability is also 1/2. If I'm doing repeated trials of rolling a die, and 3 is success, that means this is what I'm looking for. This is what I'm looking for. So the probability of getting a 3 is 1/6. The probability of not getting a 3 is 5/6. And the third example, the probability of picking a face card from a standard deck of cards. So in a standard deck of cards, there are 12 face cards. This is my success, getting a face card. So that would be 12 out of 52. And the probability of not getting a face card, 40 out of 52. You may have noticed in each of these, you're really looking at complementary situations. So these always add up to 1. 1/6 and 5/6. 1. 12 over 52 and 40 over 52. 1. Remember the word complements from yesterday. So these experiments, their outcomes are random. And again, we're looking for success, and we're looking for failure. And yeah, here's that mathematician's name, Jacob Bernoulli. These particular problems follow this formula right here. And you do need to memorize this. So this is something you want to put right on your formula page. It's n choose r, p to the r power, and q to the n minus r power, where each of these are defined as follows. N choose r, you're going to use your calculator for. The value of n is the number of trials, or the number of times you're repeating the experiment. R is the particular number of successes you are looking for. P is the probability of that success, and Q is its complement, the probability of failure. The best way to get good at these is to try a bunch of problems. Now, before we go into the way that we typically do them, we do want to explain what's happening. So, okay. If 5 fair die are tossed, what is the probability they show exactly 3 fours? So n is the number of times I'm going to repeat the experiment. Well, 5 dice are being tossed, so I'm looking at 5 different die. R is the number of successes I'm looking for. Well, I'm looking for 3 4s, so I'm looking for 3 of those die to be the value 4. Then we need the probability of getting a 4 on a die. Q, remember, is its complement, or the probability of not getting a 4. 5 out of 6. Okay, these should always add up to 1. And those are the 4 values we need to plug into this formula up here. But before we do that, all of this is showing you an example of how this could turn out. So if we rolled 5 times and we got 3 4s, here's a 4, here's a 4, and here's a 4, then the probability of getting that first 4 is 1 out of 6. The second 4, still 1 out of 6. They're dependent. The third 4, still 1 out of 6. And then the x's stand for a number other than 6. So those probabilities are 5/6 and 5/6. Well, if you look at this, that's actually 1/6 to the 3rd power, because there's 3 of them, and 5/6 to the 2nd power. And that's exactly what our formula up above is showing us. The probability of success to the r and the probability of failure to the n minus r. So if we just think about one situation for rolling those die, I've got most of this formula done. So where does the n choose r come from? Why is this part in the formula? Well, it's in the formula because we have 5 slots or 5 different die, and we don't know which of those die is going to show a 4. So this is all the ways that 5 die can have 3 spots filled with a 4. See, 3 spots, 3 spots, 3 spots, 3 spots, 3 spots. So there's that many combinations of these die, and that is n choose r. So here's the complete formula. All right, so let's go ahead and see what that would be. Some of the work is done here for you. This comes out to 10 times 25 over 7776, which is 250 over 7776. So all of this is the background on how it happens. But what we want to be good at, really good at, every time you see one of these, I want you to do N, R, P, and Q right away. Pick out the important parts, N, R, P, and Q. And then we're going to put those into the formulas. So number 2, the probability that your team wins a game is 2/3. That's important, and that's the probability of winning. What is the probability that you will win exactly 3 out of 4 games? So we're going to play a bunch of baseball games. How many total are we playing? 4. We're looking for a certain number to win. The R value is 3, because we want to win 3 of those games. Exactly 3. So we're looking at winning. Probability of winning is given. And Q then equals 1/3. So we're going to take these numbers almost in order from top to bottom. We're going to put them into that formula. That formula is N choose R. Probability of success to the R, probability of failure to the N minus R. So from the top, it's 4 choose 3. 2/3. Just keep going down that row. Almost. 2/3. To what power? Well, I'm looking for 3 wins. Win, win, win. And 1/3, well, this is winning, this is losing. If I'm going to win 3 games, then I'm looking to lose 1 game. And that is n minus r as well. So we're going to compute this. Grab your calculator and do 4, choose 3. I'll give you a moment. Pause, try it yourself. Okay, 4 choose 3 is 4. 2/3 cubed is the same as 2 cubed over 3 cubed, 8 over 27, and 1/3 to the first is 1/3. I'm always going to use fractions here. So if you're going right to your calculator, we're going to have some issues. Here I got 4 times 8 times 1, that's 32. And on the bottom I have 81. If you're going to use your calculator over and over and over, you probably want a math frac at the end of these. Let's look at the next example. An arrow can land on one of 7 equally likely regions on a spinner. And they're numbered 1, 2, 3, 4, 5, 6, 7. So we have a spinner. Find the probability of exactly 2 evens on 3 spins. All right. There's my makeshift spinner. How many times am I spinning the spinner total? 3. How many certain events am I looking for? I'm looking for 2 times something to happen. What am I looking to happen? I'm looking for an even, for it to land on an even number. 2 is even, 4 is even, and 6 is even. So for that simple probability, the probability of landing on even is 3 out of 7. How about not even? 4 out of 7. Remember, once again, these add up to 1. They're complements. All right, let's throw it into the formula from the top. 3, choose 2. 3/7 to that same 2, because you're looking for twice 2 events to be landing on even. 4/7 to the, well, if I wanted to land on even, whoops, I can't spell, even 2 times, then I'm looking for it to land on odd out of 3 spins 1 time. All right, grab your calculator again and go ahead and do this one. I'm going to use fractions. Three choose 2 is 3. 3 squared is 9. 7 squared is 49. 4/7 is 4/7. 4/7 to the first. All right, now just multiply across the top. And across the bottom. And there we go, 108 over 343. Let's set the next couple up, and then we're going to go do these other type where we have at least or at most a number of things happening. So Dr. Glendon, the school physician, is in charge of sports physicals. He has compiled his information and has determined that the probability a student is on a team is 0.39. Dr. Glennon examined 5 students chosen at random. Find to the nearest hundredth the probability that exactly one of those 5, so we know N, we know R, will be on a team. So P is the probability you are on a team, and that is given right here, 0.39. So what is Q? Q is 0.61. 0.61. Okay, so we have decimals this time. I won't be using fractions. Let's set it up. NCR is 5, choose 1, 0.39 to the 1, 0.61 to the, if you said 4th, you're right. Okay, and you can do that one on your own. Let's set up number 5. If Parker, a star baseball player, hits 1 home run, that's how I know he's a baseball player, 1 home run for every 10 times he's at bat. So there's some numbers here, let's underline. If Parker goes to bat 5 times during tonight's game, what is the probability he will hit exactly 2 home runs to the nearest hundredth? All right, N, R, P, Q. Let's read it again carefully. N should be the number of times that he goes to bat tonight. So he's going to bat 5 times. We're looking for him to be successful with a home run. How many times? 2. Now I need the probability that he gets a home run. So that's what this first one was. Parker hits a home run for every 10 times at bat. So his probability of getting a home run is 1/10 or 0.1. You can do that either way. So the probability he doesn't get a home run is then 9/10. Okay, let's set it up. From the top, 5, choose 2. And then that probability, 0.1. I want him to get how many home runs? 2. And then the probability he doesn't get a home run. So I'm examining at 5 times at bat. If I get 2 home runs, then that means 3 of them are not home runs. That's just subtracting 5 minus 2 to get this number. Okay? You go ahead and do that one as well. We're just setting these last couple up. Okay, at least and at most. So these get a little trickier. At least, at most. First we have to examine what this means. This new question. The probability that your team wins a game is 2/3. Find the probability you will win at most 2 out of the next 6 games. All right. N, R, P, and Q. So, N, the total number of games. R, the number I am looking for wins. Now, it says at most 2. So out of 6 games, if I'm looking for at most 2 wins, that's 2 wins, or 1 win, or no wins. Notice we're using the word or. At most is the top. The probability we win is 2/3, so the probability we do not win is 1/3. Now, at most and at least require how many ever values you have for R, it requires that many parts. So we're going to go from the top. We're going to start with 6, choose 2. 6, choose 2. 2/3 squared, 1/3. So how many games would we lose out of 6? 4. And then we have to add, that's our or, and now we're going to do 6, choose 1. 6, choose 1. 2/3 to the first, 1/3 to the fifth, plus our third part, 6, choose 0. 2/3 to the 0, 1/3 to the 6th. If we don't win any games, it means we lost all 6. So these take a lot more work. They're usually worth more credit. Let's go through. Pause, get a step ahead of me. I'm going to do all fractions here, and then you can turn it back on and see if you got it right. So in my calculator, 6, choose 2 is 15. I'm going to put over 1. 2/3 squared, 2 squared, 3 squared, and 1/3 to the 4th is 1 over 3 to the 4th is 81. And I'm going to leave that and do my next part. 6, choose 1. 6, choose 1 is 6. 2/3 to the first. 1/3 to the 5th. Plus, and the last one, 6, choose 0. If I'm not taking anything, there's only one way to do it. 2/3 to the 0, also 1, and 1/3 to the 6th. So 1 to the 6th is 1, 3 to the 6th is 729. The cool thing about these is you'll get the same denominator all the way across, as long as you didn't reduce. That's why fractions are good here. And my numerator is just multiply across. 15 times 4, 6 times 2 times 1, and 1 times 1 times 1. Now we just add those numerators, and I've got 73 over 729. That's the probability that we'd win at most 2 games out of 6. Okay, let's set the next one up. The probability that your team wins a game is 2/3. What is the probability you win at least 4 of the next 6 games? N, R, P, and Q. How many games total? 6. What are we looking for? That we win at least 4. So at least 4. 4 is the least, so they get bigger. 4, 5, and 6. We don't go past 6 because we're only playing 6 games. And of course it's I win 4 games or 5 games or 6 games. The probability that we win, not win, 1/3. So setting this one up, hopefully you're doing well. Gonna finish it up here from the top. 6, choose 4. Probability to the 4th. Losing. How many games would you lose if you won 4 out of 6? 2. Or 6, choose 5. 5 wins is my exponent. So how many losses? Or 6, choose 6. 6 times winning, that means no losses. And I'll let you finish that one up. We can do a couple more tomorrow. These are real common on Regents exams, so you want to be good at these. See you tomorrow.